Now, joint arrays. We can have two types of joint arrays, systematic and non-systematic. Pretty straightforward names, kind of self-explanatory, but I'm obviously going to explain anyways. So a systematic joint is where there's a regular pattern, they're parallel to each other, they're primary joints, and you can see this repeating rows of parallel joints. Non-systematic is not parallel, odd angles, not necessarily through going, and so forth. So when we have these planar parallel joints, or at least subparallel, so close to parallel, they're systematic. For example, here on the right, you can see Devil's Tower, one of the most famous examples of regular systematic jointing. A special case, which we'll talk about shortly, for the exact type of systematic jointing. But you can see that the joints are very close to parallel. Even where they curve, they're all curving to match each other. Irregular jointing, on the other hand, here filled with a white mineral, making it easier to see, so now it is a vein, but at the time that it cracked, before the mineral filled it in, it was an irregular, non-systematic joint array. Now, joint sets and joint systems. A joint set is a group of systematic joints. So not the non-systematic, only the systematic. So if you've got a set of these parallel joints, it's a joint set. A joint system is when two or more joint sets intersect. So that means they must be at two different angles. This implies changes in stress over time. That's important. Looking at this from either a geological or an engineering standpoint, this tells you something about the stress field and what's happened in the past, how the rock is going to behave, and so forth. Now, the angle between two of the joint sets, whether there's just 2 or 3 or 20, the angle is the dihedral angle. The type of joints that we can look at, or joint systems rather, are orthogonal, conjugate, sigmoidal, columnar, and J-joints. Now we'll look at these individually. Here you can see a chart from your book showing some orthogonals. There's 3 of them there, where orthogonal terminology that we are familiar with from math and physics and so forth means perpendicular. Same thing also as normal. Here, instead of using normal, we use orthogonal to make it more clear what we're talking about. You can see that they can be through going in both directions, like in the top. They can be through going in one direction and then just between the joints in the other direction, like in the middle. Or at the bottom, none of them are through going, but they're still all perpendicular to each other. There are a bunch of joints that are all in the up-down direction and a bunch of joints that are in the side-to-side direction, so they are parallel to each other within each set, even though they're not through going. So they are systematic joints. Now in the top center, we have conjugate joints. They're either through going or close to through going, both parallel within each set, but they're at some angle other than 90 degrees, so they're not orthogonal. Very commonly, it's pretty close to a 60-120 relationship. You can see here, the small angle within any of those little parallelograms is about 60 degrees. The bigger angle is about 120. Now, sigmoidal joints are pretty close to the conjugate joints, except you notice there's some curvature. Within any one of these joints that's at an angle, still a set because they are parallel to each other, but the ends of each joint curve and start going parallel to the primary through going side-to-side joints. At the bottom of this middle block is another type of sigmoidal where it looks almost more like the conjugate, except we're not getting all this through-going jointing, and that gets classified as the sigmoidal. But this one right here in the center is the classic sigmoidal, so that's the look you want to remember. J joints up here on the top right are very similar to the sigmoidal, except instead of the ends of the angled joints curving parallel to the large through-going joints, they curve opposite so that they hit them perpendicular. So, oops, where's my mouse? You can see here, we've got a nice angle, and then right at the end it curves and hits the big joint at 90 degrees. Those are J joints. Then columnar joints can be very hexagonal, like this at the bottom right, or close to hexagonal with some pentagons or maybe some septagons, 5 and 7-sided, but vaguely hexagonal. So they don't have to be perfect, they can be close with some 5 and 7 sides, because these are not cleavage breaks like in a mineral, so we can have this irregular. These are just joints from the rock cooling and contracting and creating tension within it, and it cracks and connects and ends up looking like this. We can also have joint arrays and joint systems in folded or bent rock. So if we had maybe a sandstone layer, and there's some stress and some folding, the rock doesn't fold perfectly, it fractures very, very commonly. And so then we can have them in different orientations relative to the fold. And here in the center you can see a little ABC axis. It's sort of like an XYZ, except in this case C is vertical relative to the hinge or fold point in the rock. Later when we get into studying folds, we'll cover that in more detail. But if you took a piece of paper and you fold it in half, that crease is basically the hinge, and C is pointing up straight out of that hinge, B is right along that fold, and A is out away from the fold along the paper. Now you can see these AC joints. They're cracked through the rock vertically, and they follow the line of A from side to side. BC joints crack vertically straight through in the C direction and then follow it side to side in the B direction. On the other hand, there are these HK0 that just go through at some random angle. And then we have ones that are if we look at it from the side, in the curvature area, they're kind of fanning around the fold. Makes sense. You fold something thick and fairly rigid and brittle, even though it's folding, there's breaking going on, and it's breaking in a kind of fan pattern. Again, there are different ways that that can happen that we get into later, but for right now, just think of it as kind of a fan pattern. And these BC joints are called strike parallel joints, because if say this started folded underground, ground surface erodes down until the rock starts to show this layer at the surface, the strike would be in that B direction. You would see a long line, a long stripe of this rock exposed. That's your strike. And so those joints are parallel to that strike. The AC joints and these crooked ones are cross strike joints because they cut across the strike of the rock. Now, this is important because in an outcrop, you don't always have everything. But if you're looking at the joints and you see a fan pattern and you see the orientation of them, you can often figure out what direction the fold took place. It can tell you about the structure just by looking at the joints. So you're looking at a small area and interpreting to understand a bigger area. In an idealized arrangement of joint arrays, you have a few different things. It doesn't always work out like this. This is idealized. But if you have through-going joints continuous through the rock, they're the master joints. They're the primary, the big joints that everything else is interacting with. Cross joints are the joints between the continuous joints. So in the sigmoidal and J, those are the ones that are at the angles and connecting these big through-going master joints. Strike parallel joints are ones that are parallel to the strike of the bed. Cross-strike joints tend to be, trend at different angles in the bedding. So they're not parallel to the strike. So again, you can see the strike parallel and cross-strike joints. Now, sheeting joints, also called exfoliating joints, happen when a plane of weakness is roughly parallel to the topography and it's unloading, basically a release of pressure creates an effective tension and the rock exfoliates. The sheets of rock break off. Sometimes they slide away, sometimes they just kind of pile up. But either way, you get this kind of exfoliation, this layered effect, this scaling almost. This is very common in large intrusive bodies, batholiths, plutons, that then get exposed at the surface, and then you get this kind of sheeting. It can happen at a smaller scale in boulders sitting outside, going through freeze-thaw cycles. The water can cause this kind of jointing as well. Columnar jointing. Previously I showed you Devil's Tower. Here, this is Giant's Causeway in Ireland. And you can see here the columnar jointing. From the side, it looks kind of like the Devil's Tower images that we see. And then, of course, if we had an aerial photo looking down on Devil's Tower, we would see the top surface look very similar to this, where it looks almost like a whole bunch of hexagonal flagstones, like you might build a pathway which is why this is called Giant's Causeway. It looks like, somebody laid a big path, walkway with some stairs and so forth because of the way the columnar joints broke up the rock. This happens in shallow, intrusive rock bodies, and when they fracture and create these joints, as they cool and contract, if it breaks into hexagonal cross sections, we call it columnar jointing.